Hi everyone, welcome back to Chem Help ASAP. Today we're going to be talking about kinetics, and specifically we're going to be going over second order integrated rate law. Let's get started. So suppose we have a reaction, A going to B. How do we write just the general rate law? Well, here is our general rate law where we're monitoring the decrease in concentration of A. That's why we have a negative here. Of course, every general rate law, you have an exponent here. Because we know this is a second order rate law, that value of N becomes 2. So our specific rate law for, again, this general reaction that we know is second order goes to A squared. Remember, the rate law as we have written it here, where we are relating rate to concentration, is our differential rate law. We want to talk about the integrated rate law, so we are going to take this expression and we are going to integrate it. This is why I have changed my deltas to d's. We need to do a little bit of calculus. When we do that, we get this rate law right here, which allows us to relate concentration to time. This is our integrated rate law. Now, one of the cool things about the integrated rate law is we can plot this with a linear plot. So let's take a closer look at all of these elements. Rewriting our integrated rate law up top, we want to show that this is in the form y equals mx plus b. So let's define each of these elements in our integrated second order rate law. Moving left to right over the equation, what is our y value? It is this 1 over the concentration of A. So we'll write that out right down here. Our m and our x match up with our k and our t. Specifically, our x value is our values of t, and our slope, our m value, is our rate law constant. So x is equal to t, and our slope, or our m, is equal to k. We have our y-intercept, or our b value, which is simply 1 over our initial concentration of A, and we will just write that right down here. So if we plot time versus 1 over concentration, we will get a linear plot. Let's see how this works with an example. Here is the reaction we are monitoring. And specifically, if you look at my data table, we are monitoring the decrease in concentration of our reactant, our C4H6. And we are monitoring how that concentration decreases over time. Now remember, for our integrated second order rate law, we need to monitor not just concentration, but 1 over concentration, or the reciprocal of concentration. So I am going to create a third column in my data table where I'm going to take my concentration and just calculate the reciprocal. So here is my final data table. You'll notice I've calculated 1 over concentration here on the very far right. At this point, I am ready to create my plot. Again, where time is my x variable or my independent variable, and 1 over concentration is my y or my dependent variable. So let's see what this plot looks like, and let's see what the equation of the line is. All right, here is my plot. Again, I am plotting 1 over concentration versus time. So you'll notice my time down here at the x-axis and 1 over concentration at the y-axis. And yes, I get a very nice linear plot. And you can use any spreadsheet application to give you this equation of the line. So I have a plot which is linear, and I have an equation of a line. What am I going to do with this? Well, I know that the slope of this line is equal to my rate constant. So that is simply my 0.0610. My intercept, of course, gives me my reciprocal of my initial concentration right over here. So again, here's my intercept at 0.9944. And then I can do a quick calculation if I want to actually get my initial concentration, which is going to be 1.006. Now, you might be saying, wait a second, don't you already have your initial concentration in your data table? And actually, no, you do not, because what is my first data point right here? My first data point is at time equals 10 seconds. I don't have a concentration at time equals 0 seconds. But using my equation of the line, I can calculate that initial concentration. And it makes sense. The concentration is greater than my concentration at 10 seconds. So yes, this does make sense for initial concentration to be about 1 molar, when at 10 seconds, my concentration was about 0.6 molar. All right, but let's say we wanted to calculate the concentration of C4H6 at 2 minutes. You'll notice I do not have that in my data table. I only go to 36 seconds. But because we have our plot and we know our K and we know our intercept, we can calculate this concentration. The first thing we need to be careful about is we want a concentration at 2 minutes. But notice the units in your data table. This is given in seconds. So the very, very first calculation we want to do is we want to convert that minutes to seconds. So here is 2 minutes. Of course, it's just 120 seconds. But this is a very commonplace for students to end up with the wrong answer in their calculation. You must watch those units. Now I'm ready to take my second order rate law. Right here, you notice that instead of writing A, I actually put in my reactants, my C4H6. Here's my initial concentration. Let's plug in what we know. Well, we don't know what my actual concentration is. That's what we're trying to calculate. So it makes sense that we don't know the left-hand side of the equation. I know my value of K. I wrote it right up here. It's 0.0610. For my time value, again, I want this at 2 minutes or 120 seconds, so I put my 120 seconds right here, plus my initial concentration of C4H6, or the reciprocal of that, which again I calculated my initial concentration, so I'm going to put that right there. Or if you like, you actually do have this whole value as 0.9944. Either way, mathematically, it's exactly the same. So at this point, I can calculate, first I'll calculate just my reciprocal of my concentration. And for that, I get 0.831. Of course, it's very easy then to just get our actual concentration, and we get our concentration as 0.120 molar. Now, does that make sense with the data we have? Well, yes, after 2 minutes or 120 seconds, our concentration ought to be much lower than 0.313, which is where it was at 36 seconds. So in the context of the problem, yes, this calculation does make sense. So you'll notice we can get all of this information simply from a data table with concentration and time data. I hope you found this video helpful, and thanks so much for watching.